Hello, it's Keith here, and this is lesson 2 of the Photon series of my 68,000 assembly programming tutorials. What's Photon? Well, it's this little thing here. It's my clone of sort of Tron. It's a very simple little game. You're this line, you've got to block this other line, and if you make it crash, you win, and if you don't, you lose. So a very simple game, but the point of the game is really about pixel plotting, because what we're doing is we're writing pixel plotting routines on all of these different systems that have quirky screens, and we're working out how to draw a pixel and read a pixel back, because drawing a pixel is of course the line you're seeing being created here, and reading a pixel back is when we work out when I do something silly like that and die. So we're going to be looking at that in our code today. Okay, so today we'll be looking at the Atari ST version. Now the Atari ST version isn't massively difficult, but basically the challenge of it is it works in bit planes, and it works with word-based bit planes, so that 16 consecutive pixels are stored in one word. The bit plane 0, the bit 0s effectively of all the pixels, is stored in one word, and then the bit 1s, and then the bit 2s, and then the bit 3s, and we're going to see that in our code. Okay, let's go over and let's take a look. So here's the Atari ST version. Now the start of the game has some definitions. Most of the code is multi-platform, so we need to configure the game for this particular system. Now this system's got no color limitations, so we can use all of the required 4 colors, excluding black, for the game. So we've got them defined there. And the game is on a 320 by 200 screen, so we've got that defined. And we're defining the screen width as 40 bytes. That basically means we're using the larger scaling of everything. So that's just setting up the alignment of some things. And here we've got a generic starting for our game. Now this is the same as in Yquest and the Simple series, so I'm not going to cover it again. And then we're setting up our colours for our graphics here, and you can see we're setting things up there for our game colours. Now what we're doing next is we're enabling the joysticks, and we're using the joystick interrupt handler, basically reading in from the joysticks and storing in some variables. Again, the same as Yquest, so if you need to know how to do that, please see Yquest or the Simple series. I did a simple joystick example there where we covered all of that. We're not going to cover them again today. Next, what we're doing is we're getting the game ready for play. We've defined some user RAM here. I believe it's right at the bottom here. Here it is. It's in this area here in the BSS section. Now that will probably define to 0, but we don't want to make any assumptions. And so we're using this CLDIR routine, which is something I've written, and it will clear, in this case, we're clearing 256 bytes of user RAM. That's all the game uses. It uses very little memory, this game. It's a simple game. And then we show the main menu, which is multi-platform code, so there's nothing else here to see for it. Now we're into the main loop here. Now if I just start up the game, and we need to maybe discuss some of the game logic so you understand what's going on. I've got the game up here. Now the game, basically the directions are only read when you press and release. I'm holding down my direction there, but I've only moved once. I have to press and release to turn again, and that's so we don't accidentally collide into ourselves. The other thing is there's a boost mode. If I press the fire button, I will start moving faster, and you can see the counter in the bottom left go down. This makes me move faster than the CPU, and that means I can catch up with the CPU and try and head him off at the pass, so to speak. So those are 2 little functions that we just needed to discuss there, because we're basically going to see them in the code. So that's what's going on there. Now here you can see we're taking the game tick and we're updating it, and we are limiting it to being either 0 or 1. This relates to that boost mode. If boost mode's on, we update the game player position every tick. If it's off, we update every other tick. But we have to update that boost counter, and unfortunately it's a little bit slow. So what we're doing here is we're setting a delay, but we're setting the delay to be a lower amount if boost mode is on. That's not to make the game faster, that's to compensate for the movement for the drawing of that font. So a bit unfortunate there, but the font does have the advantage of being scalable and working on all systems of all shapes and sizes. So the font does have its benefits over a raster font, but a vector font is slow to draw. Okay, we're then setting up a key buffer here. We're setting it to be no keys pressed, and we're testing the keys and seeing if anything has been pressed. And if nothing's been pressed, we're going to jump to here and we're going to clear that key timeout, and that means that any future presses will be responded to. We're then storing the presses in D2, which is our sort of buffer here for this loop. We are then decreasing our loop here. It's called pause BC because it was using BC on the Z80 version. It's in this case we're actually using D1 here, but we're just keeping that loop counter going, and that's just reading our joystick in here. Now we're ready to start actually processing those joystick keys. But what we're doing first is we're checking if the key timeout is still set. If it is, then the player never released the direction, and so we're going to ignore the presses, and we do that just by skipping down to here. What we do next is we turn boost mode off here. Now we might turn it on later. We do that by writing a 1 to the boost variable. We're then setting A3 to player direction here. We will need to change that if the player is turning. We also set player acceleration to A6 here, and that is because we will need to set that to the correct accelerations depending on the move if the player has turned, and that's done here. What we do next is we're testing the direction keys, the left and right here, and we are either decreasing or increasing the player direction, and then we're running this set player direction routine to do the rest of the work. And the final thing we're doing is setting the key timeout to E90, and that will of course disable the keys until next time. Here we're checking the fire button. If the fire button is pressed, we see if there's any boost power left. If there is, then we turn boost power on by clearing the boost variable here. We don't actually decrease the boost power because we actually do that as part of the handle player routine. Another thing to notice is we are not actually setting the timeout for the boost power because we need to be able to hold that down to be able to move faster. Finally, what we're doing here is we're running the player handling routine here, which updates the player position and collision detection, and then the CPU routine here, which does the same for the CPU player. And we just loop all the way back to the top. So this is really the main game loop, very small as you can see, because most of the game's code is in the multi-platform section, which is where we want it to be. Okay, now we're going to look at the PSET routine, which is the pixel drawing routine for drawing an individual dot based on an X, Y coordinate and a colour. D1 is the X position, D4 is the Y position, and D2 is the colour. First, what we're doing is we're using get screen pos here, and this will calculate a byte position of the pixel we're interested in. You can see we're doing this here. This is almost the same as the version we used before in Yquest. What we're doing here is we're ignoring the bottom 3 bits because there are 8 pixels in a byte, so that's 3 bits of the X coordinate we want to skip for calculating the byte screen position. We're then taking the screen base, which is going to be somewhere in memory. We've defined that earlier. And then we are calculating the word position with these bits of the X coordinate here. And then we are calculating the position within that word, either the low or the high byte, with this bit here. And that's calculating the X position for us. The Y position is much easier. We just multiply by 160 because there's 160 bytes per line, 320 pixels per line, and of course 1 nibble per pixel because it's a 16 color screen. So that's why it's 160 we're multiplying the Y coordinate by. But this basically gets a byte position for the XY coordinate we want, but we then need to work on one of those pixels within that byte. And that's what we're doing here. We've got a lookup table here for each of the 8 potential pixels within that byte that we might want to change it. So you can see one of the bits is set depending on that pixel position. So we're just taking the bottom 3 bits of the X coordinate and reading in one of those masks here. We're storing that into D1. There's actually a typo here. These are backwards. Sorry about that. So we're storing the mask for the background in D1 because we're flipping the bits here, and that will set that to be a mask to keep the background pixels. And then we're loading in a mask for the pixel we want to change so that we can set the colors of the bit planes here. So that's what we're doing there. Now what we're going to do next is we're going to read in the bytes from each of the bit planes, and we're going to potentially set that pixel or clear it depending on if we need to set that pixel depending on the color that was specified to us in D2. So what we're doing here is we're loading in the current pixel here. We're then masking with the background mask here that we set here, and that's removing the pixel. Then we're testing the lowest bit of D2 by rotation here, and we're seeing if we get a 1. If we do get a 1, we need to set that bit, and we're doing that by ORing the mask of the pixel here that we got in D3 here. And so that would set bit 0 to 1 if we run that bit. If we don't run that bit and we just do this AND, it would set it to 0. So that's bit plane 0 here. We then move to bit plane 1, and we do that by adding 2 because there's 2 bytes per word, and as I say, the 4-bit planes are in 4 separate words. So we add 2 there to our memory address, and we do the same for bit plane 1. Then we do the same for bit plane 2, and finally we do it for bit plane 3. That's all 4 bit planes, so that gives us the potential for all 16 colors here, even though this game doesn't use it. Now the point routine is almost exactly the same. We are using get screen pos again. We're using that pixel lookup, but this time we're kind of reversing the procedure. We have D0 as a build up here, and we are testing the pixel that we want to look at here from each of the bit planes and seeing if that pixel the bit of that pixel is a 1 or a 0. If it's a 1, then we're setting the respective bit of the build up here in D0. So 1 for bit 0, 2 for bit plane 1, 4 for bit plane 2, and 8 for bit plane 3, and the combination of this would make the color. Now, the game we're looking at here, Photon doesn't actually look at the colors, it just looks at black or not black, but this code should be able to calculate the correct color if you were doing something more advanced. We've got our joystick routine here. As I say, this is exactly the same as before in the simple series, so we're not going to cover it. And finally, we've just got a simple clear screen routine here, just clears the screen memory, clears all the bytes there, and that's really all there is to it. As I say always, you can go to my website and you can download today's source code, so you can hopefully build it yourself, and if you somehow manage to make any good use of it, good luck to you. You're welcome to do so. You don't need to give me any credit or anything, because it's supposed to be there for you to benefit from. So, have a play with it, and if you manage to make something out of it, great. Anyway, we're going to be going over various other 68,000 systems here, some of them bitmap based like the Amiga next time, and some of them distinctly not bitmap based like the Neo Geo, so you'll have to wait to see how I've managed to do that. Anyway, I hope you've enjoyed this today. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.